Hi, this is Ashwin, and this is my New Year quiz video. So, problem one. Problem one was as follows. A person is pushing cargo onto a ship. The cargo's mass is 200 kgs and is being pushed up a 30-degree ramp. The coefficients of friction between the cargo and the ramp are mu static, which is equal to 0.5, and mu kinetic, which is equal to 0.3. If the cargo is pushed with the minimum force required to move it and break static friction, then continues pushing with this force, what would its acceleration be up the ramp in meters per second squared? So the first step in this kind of problem is to draw out the force diagram. Furthermore, it would be helpful if you drew two diagrams, one to represent the applied force needed to move the object, and the second to represent the object in motion. For the first diagram, we need to draw all the forces acting on the box at the moment when the force is applied. As always, the force of gravity acts straight down, and the normal force supports the block on the surface. The gravitational force, or mg, can be broken down into two perpendicular components. The component perpendicular to the surface is equal to the gravitational force multiplied by cosine theta, or mg cosine theta. This is also equal to the normal force. The component parallel to the surface of the inclined plane is equal to the gravitational force multiplied by sine theta, or mg sine theta. Now that the force diagram is drawn, we need to set up our first equation. Since the applied force is directed upwards, the inclined plane, the force of friction, represented by the perpendicular gravitational component, or the normal force, multiplied by the coefficient of static friction, acts in the opposite direction. In addition, the parallel component, or mg sine theta, is directed downwards to the inclined plane in the same direction as the force of friction. Therefore, our equation is force applied minus mg sine theta minus mu s mg cosine theta is equal to ma. Since this first equation represents the moment at which the force is applied, the acceleration can be set to 0. Hence, the equation can be simplified to F applied is equal to mg sine theta plus mu s mg cosine theta. The second diagram will have similar labeled forces as the first. The only key difference is with the force of friction while the object is in motion. The coefficient of friction between the cargo and the ramp is different when the object is in motion, and hence is represented by mu k rather than mu s. The second equation, representing the object while in motion, would be as follows. F applied minus mg sine theta minus mu k mg cosine theta is equal to ma. And here are two equations, and we can substitute the value of F applied from the first equation into the second equation to get the following. Mu s mg cosine theta minus mu k mg cosine theta is equal to ma. By substituting values and isolating the variable a, the answer to this question is 1.7 meters per second squared. Alright, now on to problem 2. Problem 2 was as follows. You throw an aerodynamic object away from Earth with an initial velocity v, and it rises to a height h before falling back to Earth. If you throw instead with initial velocity 5v, by what factor will the height it rises to change? The first step is to draw the diagram. As seen in this diagram, an object is thrown up at a velocity of v, reaches a maximum height h, and then falls back to the ground. One important thing to note is that at the maximum height, the velocity is always equal to 0. So how do we determine the change in maximum height if the ball is thrown with an initial velocity of 5v? Well, we must use kinematics. The equation that I used to solve this problem was vf squared minus vi squared is equal to 2as, with s being the vertical displacement and a representing the acceleration of the object, which in this case was gravity, or negative 9.8 meters per second squared. So first, I isolated h by assuming that the initial velocity was equal to v. Since vf is always 0, I obtained the following equation. S is equal to minus v squared over 2a. Next, I'll assign my initial velocity as 5v and substitute that value into the kinematic equation above. Once again, vf is at a maximum. vf is 0 at the maximum height. And now here's the work. So 0 squared minus 5v whole squared is equal to 2as. Then simplify to negative 25v squared is equal to 2as. And and S is equal to negative 25v squared over 2a. By comparing the two equations, we see that the height is 25 times as high when the initial velocity of the projectile is multiplied by. Alright, now on to problem 3. Problem 3 was as follows. The figure shows two boxes with M1 being greater than M2 that are on a level frictionless surface. We apply a horizontal force either towards the right on M1 or towards the left on M2. Determine if and how the magnitude of the force between each is A, 0 newtons in either case, B, larger if F is applied to the right, C, the same in either case, and D, larger if F is applied towards the left. So in this problem, we must first draw two force diagrams, one for each direction in which the force is applied. In my first diagram, the applied force represented by F was exerted on the heavier block. This caused box 1 and box 2 to exert an equal force on each other. This is labeled as F1 in this diagram. The next step is to create equations representing this scenario. Using Newton's second law, we know that m1 plus m2, or the overall mass of the system, times the acceleration is equal to F. Rearranging our system, we get A is equal to F over m1 plus m2. After that, I would isolate m2 and use Newton's second law to write an equation representing F1. This equation is F1 is equal to m2a. One important thing to note is that the acceleration of the individual block, or m2 in this case, is the same as the acceleration of the entire system. So hence, we can substitute a in. So by substitution, we find that F1 is equal to m2f divided by m1 plus m2. So the same steps apply when we create the second diagram. As seen in this diagram, the applied force is exerted on the lighter block, causing box 1 and box 2 to exert an equal force on each other. This force is labeled as F2 in this diagram. And the equations for this scenario is also very similar to the previous one. The equation of acceleration of the overall system is the same. A is equal to F over m1 plus m2. However, this time we isolate m1 and use Newton's second law to write an equation representing F2. This equation is F2 is equal to m1. By substitution, we find that F2 is equal to m1f divided by m1 plus m2. And now we have to compare. By comparing the two values of F1 and F2, we see that F2 is greater than F1, since M1 is greater than M2, and both are in the numerators. And the denominators are the same. Since M1 is greater than M2, F is larger if applied to the block with a smaller mass. Alright, so now on to problem 4. Problem 4 was as follows. A projectile is fired from the edge of a 20-meter high cliff. The initial velocity components are 940 meters per second horizontal and 96 meters per second in the y direction. The projectile reaches a maximum height at point P, which is here, and then falls and strikes the ground at point Q, which is here. So how high is point P above point Q? And these additional air resistance. So the first step in solving this problem is to draw a diagram, which is shown here. As shown in the diagram, the projectile is at an initial height of 20 meters. The maximum point is at P. The ground is point Q. So in order to solve this problem, I calculated the distance from the top of the cliff to its maximum height. I did this by utilizing the kinematic equation Vf squared minus Vi squared is equal to 2As. The initial velocity in the vertical direction is 96 meters per second, and the final velocity at the projectile's maximum height, or P, is 0. And the acceleration is equal to gravity, which is negative 9.8 meters per second squared. So by substituting values, I found that S is equal to 470, meaning that the distance from the top of the cliff to the maximum height of the projectile was 470 meters. However, this is not the final answer. We need to make sure to add the 20-meter distance, as you can see back here, from the top of the cliff to point Q. Hence, the distance between point P and point Q is 490 meters. All right, now problems 5, 6, and 7. These problems are all interconnected and based on the same scenario. So the scenario is as follows. 4 blocks of equal mass and size A, B, C, D, are on horizontal shelf on Earth, so all masses are at the same height. Mass A falls from rest, mass B has an initial velocity towards Earth, mass C has an initial velocity away from Earth, and mass D has an initial velocity horizontal, parallel to the shelf. Our task is to order the objects based on the time they land on the ground. So the first step, like in previous problems, is to draw a diagram and label the forces. As stated in the problem, all four blocks start at the same elevation, as you can see here. The initial velocity of mass A is 0 in the vertical direction. The initial velocity of mass B is directed downwards towards the ground. The initial velocity of mass C is directed upwards, away from the center of the Earth. And the initial velocity of mass D only has a horizontal velocity, meaning that its vertical velocity, which is the key velocity where we need to focus on in this problem, is 0, making it the same as mass D's. One important concept to note is that the acceleration in this problem is gravity, which is directed downwards towards the Earth. Since the initial velocity of B is the same as in the direction as gravity, that mass will reach the ground first. Since mass A and D have the starting initial velocity of 0, they will reach the ground after mass B and at the same time. Finally, since the initial velocity of mass C is directed upwards, opposing the acceleration of gravity, it will be the last block to reach the ground. And these are the final answers. And so that's it for the quiz.